Good morning, good afternoon, good evening. This is Mr. Payne bringing you Unit 6A, Lesson 4, Geometric Sequences. We're going to talk about exercise number 1 and review real quick the arithmetic sequence just to remember what we're talking about here and the difference between the arithmetic sequence and the geometric sequence. So let's bear with me here. It says find the next three terms of the sequence. Well, whenever I read that, what did I ask you to do is I'm going to ask you to create a table. So I'm going to say x and y, and I'm going to ask for the next three terms. Well, if I start with a sub 1, which is 1, I want to go 3 more. So 2, 3, 4. A sub 1 is 5. And then I look at my pattern. Okay, it says talking recursively. This is a recursive pattern because it says n minus 1 down there. So that's how I know it's a recursive formula. And I'm changing by adding 3 each time. So I'm going to say 5 plus 3, which is going to give me 8. 8 plus 3, which is going to give me 11. And 11 plus 3 gives me 14. Now B says find the value of a sub 20 without listing out all the 20 terms. So the problem that we have here is that we cannot use the recursive formula. Why can't we use the recursive formula? Because we don't know what a sub 19 is. And it says don't go ahead and do the table out 20. So how can we do that? Well, we are given a table. So we have to remember that if we're given a table, we can write an equation from a table. There's a couple different ways I've taught you how to do that. We can back this up. We got to get to 0. So if I'm adding 3 going down, if I go up, I'm going to subtract 3. So 5 minus 3 gives me 2. What does that identify, Mr. Payne? Well, that identifies my y-intercept. So now I can say, okay, a sub n has a y-intercept of 2. And we know what my slope is. My slope is determined right from my recursive formula, and my slope is 3. So my formula is a sub n equals 3n plus 2. Wasn't that easy to create an explicit formula? I think so. So now we're going to take that 20 and we're going to plug it right in for my n's. So a sub 20 equals 3 times 20 plus 2. Remember, all this can also be done on your calculator. If you don't remember on how to set up an equation, could we have not typed that in as a list? Both of those in as a list. Stat calc 4, because we're talking about a linear function. Absolutely. So a sub 20 equals 62. Clearly, arithmetic sequences share many characteristics of linear functions. In fact, arithmetic sequences are examples of discrete linear functions. Exponential functions have their own discrete versions, and those are called geometric sequences. They have a very simple recursive definition, and they do. The recursive definition is very nice and easy for the geometric sequence. Given the first term a sub 1, then each successive term can be found by saying a sub I equals a sub I minus 1 times r, where r is some constant often known as a common ratio of sequence. For each of the following geometric sequences, identify the common ratio. So the common ratio is what I'm multiplying by, and given the next two terms. Okay, so how did I go from 2 to 6, 6 to 18? Well, hopefully you look at that and say, okay, Mr. Payne, I was able to multiply by 3. Well, 18 times 3 is 54. 54 times 3 is 162. So my ratio is 3. Let's look at B. How am I going from 4 to negative 20, negative 20 to 100? Well, I'm multiplying by negative 5. So 100 times negative 5 is going to give me a negative 500. Negative 500 times negative 5 is going to give me 2,500, and it's going to be a positive. So my common ratio is negative 5. And then C. How am I going from 16 to 8 to 4? Well, I hope that you notice that we're cutting it in half. I'm sorry. Yeah, we're cutting it in half. And that my common ratio is going to be 1/2 because I'm going down. So I'm decaying. And 4 divided by 2 is going to give me 2. 2 divided by 2 is going to give me 1. So my common ratio is 1/2. As with arithmetic sequences, we should be able to predict any particular term in the geometric sequence by thinking about how many times we have multiplied by the common ratio. All right, exercise number 3. Consider the geometric sequence given by the recursive formula. B sub 1 equals 3, and B sub n equals B sub n minus 1 times 2. Find B sub 2, B sub 3, and B sub 4. Write each as an extended product to see a pattern, but also find the final results. So, right away, create your table. Here's my x, here's my y. I want 1, 2, 3, 4. Don't forget, these are my terms still. My 1, 2, 3, 4, those are called my terms. Okay? Now, I know B sub 1 is 3. Now what we have to calculate is what B sub 2 is. Remember, this is what it looks like. So I'm going to say B sub 2 equals B sub 2 minus 1 times 2. Well, B sub 2 equals, what is 2 minus 1? B sub 1 times 2. Well, what is B sub 1? B sub 1 is 3. 3 times 2 is 6. So B sub 2 equals 6. What I want you to notice is that you're taking the 1 before it and multiplying it by 2. So what is 6 times 2? 12. 12 times 2 is 24. And so forth. Well, based on A, determine the value of B sub 10 and B sub 20. Well, we could continue that out all the way. Or we can figure out a new formula by using that information. We can say, okay, A sub n equals A sub 1 times my rate raised to the n minus 1 power. Now, I know that I taught you before that that n minus 1 is the recursive part of it, okay? But it's when A sub n minus 1. When it's down below or written like that, B sub n minus 1, when it's that little one, that's when we're talking recursive. Up here, it still means recursive, but what we're doing is we're going to raise it to that power that was right before it. So does that make sense? Let's take a look at this. If I wanted to use this formula here to find these patterns, watch what I'm going to do. I'm going to say, okay, in order to find how many times did I multiply to get my third term? Well, I multiplied it 2 times. I had to multiply it here by 2. I had to multiply there by 2 in order to get my third term, right? So you're always taking one less than you're looking for. So that's what we're going to do. So A sub 1 is 3 times my ratio, common ratio, which is 2. R is common ratio, don't forget. Raised to the, well, if I'm looking for 10, I'm going to say, okay, 10 minus 1, which is really 3 times 2 raised to the 9th power. If you do that in your calculator, I hope that you can figure out that 3 times 2 raised to the 9th power is 1,536. And the last one says B sub 20. You're going to say, okay, A sub n equals A sub 1, which is 3, times my common ratio, which is 2, raised to the 20th minus 1. Okay, 20 minus 1 is 19. So 3 times 2 raised to the 19th power, which is going to come out to be 1,048,556. It's a pretty large number. All right, one thing you might have noticed in the last exercise is how quickly a geometric sequence can grow. You're absolutely correct. It grows very quickly. That's why it's called the exponential, and it's linked with exponential. Does this sound familiar? Let's take a look at a classic problem. Exercise number 4. You have just won a very strange lottery. The lottery promises to give you money each day for a 30-day month based on 2 options. Option number 1, you can receive $1,000 on the first day, $2,000 on the second day, $3,000 on the third day. In this arithmetic sequence, so what am I doing each day? I'm adding 1 day, right? So I could say that if I wanted to write an equation for that, option number 1, I'm going to do 2 sides. Option number 1, if I did a table, right? What does that look like? 1 is 1,000. 2 is 2,000. 3 is 3,000. 4 is 4,000. What am I really doing? I'm multiplying by my term by $1,000. I'm increasing by 1,000, right? So I can write in a formula that says y equals $1,000 times my x, whatever x may be. Okay? So that's the formula for option number 1. Option number 2 says you could receive 1 penny for the first day, 2 pennies for the second day, 4 pennies for the third day, 8 cents on the fourth day, etc. for the geometric sequence. So if I did a quick table on that guy, what would that look like? I said, okay, 1 would be 0.01, 2 would be 0.02, 3 would be 0.04, because I'm doubling each time, right? I notice that I'm doubling each time, 0.08. And this is a geometric sequence. So if I took that geometric formula that I just taught you, and I said, okay, so a sub 1 times my rate raised to the n minus 1 power. So what is a sub 1 going to be? My a sub 1 is 0.01 times my rate, and we talked about that my rate is doubling, so times 2 raised to the, 30 minus 1. Because I'm talking about the 30th day, right? So 0.01 times 2 raised to the 29th power. Go ahead and calculate that, and I believe that you're going to get $10,737,000, $418.24. And if you did option number 1, you would do y equals 1,000 times 30 days, which gives me $30,000. So I hope that you can recognize that I would choose option number 2, because that's $10,737,418 as my better option. Graphs of geometric sequences will look familiar because they are the type of discrete exponential functions. Remember, so we're tying these together. Arithmetic goes with linear, geometric goes with exponential. For a geometric sequence defined as a sub 1 equals 16 and a sub n equals a sub n minus 1 times 1/2, list and plot the first 6 terms on the grid below. Okay, right away, create my table. How far am I going to go out? To 6. So 1, 2, 3, 4, 5, 6. You can type it right into your 16 here. And now all I'm doing is taking that 16 and multiplying it by 1/2. So what is half of 16? 8. Half of 8 is 4. Half of 4 is 2. Half of 2 is 1. Half of 1 is 1/2. I hope you were able to see that. All I'm doing is multiplying by a half. Multiply by a half. Multiply by a half. Multiply by a half. I'm multiplying by my common ratio. And if I go ahead and plot these points, 116 will give me a point way up here. 2, 8. 3, 4. 4, 2. 5, 1. 6 and 1/2. And I would draw my line just like that. So I have a common ratio, and you can see that with that exponential type function, looking function, discrete function, I have a decaying pattern. So when I multiply by a fraction, doesn't that mean that we are decaying? I hope that this is all tied together nicely from what we just talked about in Unit 6. Have a great night. If you have any questions, feel free to contact me.